One topic that many people in telecom still find confusing is how the internet actually works. You might think this is not essential knowledge, but in recent years it has become increasingly important. Mobile operators have been asking over-the-top or OTT content providers such as YouTube, Netflix and Facebook to compensate them for the large volumes of data used by their subscribers. In this video, we will explain how the internet functions behind the scenes and try to make sense of the often complex question of who pays whom and why. This diagram shows a simplified layout of the part of the internet we will be exploring in this tutorial. It highlights the various internet service providers or ISPs that connect homes, offices and factories, as well as major OTT content providers such as Facebook, YouTube and Netflix. In between, you can see several transit networks, which we will discuss in the next slide, and an Internet Exchange Point or IXP, which we will cover a little bit later. Let's take a closer look at Internet Transit Services. Home users pay ISPs to deliver their data across the globe. Businesses also purchase transit services to support their global communications. Since the internet is a global network made up of interconnected smaller networks, ISPs must connect with one another to allow their customers to communicate. Smaller ISPs often buy transit from larger, better connected ISPs. This forms what is known as a transit chain. Importantly, there are no super ISPs that cover the entire internet. Having a single global ISP would pose a major risk of single point of failure and could lead to monopoly concerns. If we return to our original internet layout diagram, the pound signs illustrate how both users and content providers pay the ISPs they are connected to. These ISPs in turn pay transit network providers to reach the wider internet. Transit networks may also pay one another unless they have a peering agreement in place, which we will cover a bit later. Let's look at an example of someone watching Netflix. In this case, the user pays their ISP, which is ISP2 in our diagram. The red line shows the path of data flowing through transit networks ISP B, D and E until it reaches the Internet Exchange Point IXP1. From Netflix side, it is connected to ISP4, which is linked to transit network ISPF, and that in turn connects to IXP1. This is shown by the purple line. In reality, most large OTT providers are also ISPs themselves and connect directly to IXPs to avoid paying large transit fees. However, for the purposes of this explanation, we'll keep things simple and stick with this example. Now we are ready to understand the concept of peering. Peering involves creating a direct connection between ISPs to exchange traffic without going through transit providers. There are two main approaches. The first is public peering, where ISPs connect to an Internet Exchange Point or IXP. This allows multiple networks to peer through a shared central connection. The second is private peering, where two ISPs set up dedicated point-to-point connection between their networks. This usually happens when the ISPs are of similar size or when they can agree on terms to handle any imbalance in data transfer. A key thing to remember is that peering is typically settlement free. ISPs do not charge each other for the traffic exchanged. This improves overall network efficiency, reduces latency, and increases resilience. Let's take a look at an example of public peering. In this case, a user connected to ISP2 is accessing Facebook. The flow of data is shown by the dotted blue line, which passes through the public peering point at ISP1. Since public peering is typically settlement free, none of the ISPs connected to ISP1 need to pay one another for this data exchange. Now, let's imagine that ISP-B and ISP-C decide it would make more sense to establish a private peering connection. In our example, YouTube is connected to ISP-B and Facebook is connected to ISP-C. By setting up a private peering link, both ISPs can reduce their transit costs and lower latency for their end users when accessing content hosted on the other network. Returning to our Facebook example, you can see that the path is much shorter thanks to the private peering between ISP-B and ISP-C. This shorter path helps reduce latency for end users accessing Facebook. It also lowers cost for the transit networks involved, and as they no longer need to rely on other transit providers where payment would be required for data exchange. One important aspect of private peering is understanding its scope. In our example, private peering between transit ISPs B and C allows them to exchange traffic only within the shaded area of the network. This means ISP-C can access networks connected directly to ISP-B, but not networks beyond that, such as those connected to ISP-D. If ISP-C tried to send traffic to ISP-D via ISP-B, then ISP-B would end up paying the transit charges, which it wants to avoid. To manage this, ISPs use Border Gateway Protocol or BGP routing policies to control how traffic is exchanged and to prevent misuse of peering arrangements. Going back to our earlier Netflix example, the transit route remains the same for users connected to ISP2, regardless of whether there's a private peering arrangement between ISP-B and ISP-C. We are now ready to talk about content delivery networks or CDNs. A CDN is a system of distributed servers that deliver web content to users based on their geographical location, helping them improve load times and reliability. CDNs offer several key advantages. First, improved performance thanks to reduced latency. By caching content closer to users, websites load faster. Second, increased reliability. By distributing content across multiple servers, CDNs ensure availability even if one server goes down. Third, cost savings. CDNs help lower bandwidth costs by offloading traffic from the origin server. And finally, enhanced security. CDNs offer protection against DDoS attacks and other cyber threats. These are just some of the reasons CDNs have become essential for improving both online performance and the overall user experience. Let's take a look at Netflix Open Connect Appliance or OCA. OCA is Netflix purpose-built content delivery network. It delivers streaming content using specialized appliances known as OCAs, which are deployed at either ISPs or Internet exchange points. These appliances cache content locally, helping reduce both latency and delivery costs, while significantly improving the user experience. According to Wikipedia, more than 1,000 ISPs have installed OCAs, enabling them to save an estimated 1.25 billion US dollars as of 2021. Netflix has also deployed OCAs at over 52 IXPs worldwide, making it easier to connect with virtually any ISP. Let's take a look at a real-world case from 2016 involving Swisscom and Netflix, a dispute that attracted a lot of attention at the time. Swisscom, one of Switzerland's largest ISPs, relied on Deutsche Telekom as a transit provider. In early 2016, Netflix shifted its traffic routing to other transit providers like Level 3 and Cogent. This change led to several severe streaming issues for Swisscom users. Video quality dropped, buffering increased, and customers began to complain. Swisscom attributed the degraded experience to Netflix's choice of transit partners, some of which were known for congested networks. As customer frustration mounted, media coverage intensified, putting pressure on Swisscom to resolve the issue. In response, Swisscom and Netflix quickly reached a direct peering agreement. This agreement improved streaming quality by allowing Netflix content to flow directly to Swisscom's network, bypassing the congested transit routes. In another case, Swisscom and Init7 were involved in a long-standing dispute over peering arrangements. Init7, a smaller Swiss ISP, advocated for zero settlement peering, where neither party pays the other for exchanging data. Swisscom, holding a dominant market position, had previously demanded payments from content providers like Init7 in return for peering access. Init7 strongly contested this approach, arguing it was unfair and anti-competitive. The Swiss Federal Communications Commission, or COMCOM, stepped in following a ruling that found Swisscom's action to be anti-competitive. This included collaboration with Deutsche Telekom to extract fees from content providers. As a result, Swisscom was ordered to establish zero settlement peering with Init7. The case also brought attention to Zatu, a Swiss-based streaming platform, which had faced similar problems under Swisscom's peering policies. These examples raised broader concerns about how dominant telecom operators could potentially abuse their market power. This is a simplified model of a typical server network infrastructure. The diagram illustrates the basic flow of how users access online services. Users connect through the internet to a backend system made up of three common types of servers: the web server, the application server, and the database or storage server. Each of these handles a different function in delivering the web service. When we talk about a content delivery network or CDN, it essentially means placing web servers closer to the end users. This allows them to access content more quickly and efficiently as the data travels a shorter distance across the network. When we talk about MEC or multi-access edge computing, it essentially involves moving the application server and the database or storage closer to the end user. This allows data to be processed locally instead of sending everything to a centralized data center. As a result, it reduces latency and improves the responsiveness of applications and services. Let us briefly look at multi-access edge computing or MEC. So MEC was originally known as mobile edge computing, but the newer term multi-access edge computing is more appropriate as it applies across a wide range of access networks, not just mobile. MEC is needed for several key reasons. The first is reduced latency. By processing data closer to the end user, MEC significantly lowers latency. This is crucial for real-time applications such as augmented reality, virtual reality, and autonomous systems. Second is improved performance. MEC enhances application performance by offloading compute tasks from centralized data centers to the edge of the network. Third is bandwidth efficiency. Handling data locally reduces the need to send large volumes of information across the network, resulting in more efficient bandwidth usage. Finally, we have enhanced security. By processing sensitive information closer to the source, MEC reduces exposure to threats during data transmission. These advantages make MEC essential for enabling the next generation of low latency, high performance digital services across many industries. Let's quickly compare MEC and CDN. As discussed, MEC brings computing power closer to the end user by processing data at the network edge. This significantly reduces latency and is ideal for real-time applications such as augmented reality, virtual reality, and the Internet of Things. A common example is that most mobile network operators now integrate U-class speed test within their MEC platforms to ensure the lowest possible latency. On the other hand, a CDN focuses on delivering static or cached content such as web pages, videos, and images from distributed servers worldwide based on the user's location. This reduces load times and enhances reliability. A similar example on the CDN side is Netflix Fast Speed Test Tool, which allows users to measure their ISP's performance in accessing Netflix content via its CDN, if one is in place. Here are some references for further learning. You can find these slides and additional materials on the 3G4G website. Thank you for watching. We hope this video has helped you better understand how the internet works, how data flows, and the important role that CDN and MEC play in improving connectivity. We would love to hear your thoughts. Please share them in the comments below. Stay tuned for more insightful content and we'll see you again soon. Goodbye.